Welcome to Learning Target 15. We are going to talk about activation energy and the Arrhenius equation in this particular video. Actually, there's going to be two videos here. We're going to break it into two parts to keep it a little bit shorter. The first part is going to talk about what is meant by activation energy of a chemical reaction. And then in part B, the next video, we'll be able to calculate activation energy using that Arrhenius equation. So here we go. First thing we're going to do here is we are going to revisit collision theory, which is a subset of kinetic molecular theory, which is what we covered in Learning Target 1 way back in September. So this little video is going to describe the three conditions that have to be fulfilled for a reaction to occur. So here we go.
Here's a beaker of cold water and a beaker of hot water. When you add sugar cubes to them, the one in the hot water will dissolve faster than the one in the cold water. To explain the different rates of reactions, Max Trotz and William Lewis came up with collision theory in the early 1900s. The first assumption of collision theory is that the particles must collide with one another in order to react. Most particles will act like billiard balls in a game of pool, and when they collide, they bounce off each other. The collision itself isn't all that's needed for a reaction to occur. The particles also need to have enough energy, enough speed, to break and form new bonds when they collide. The minimum energy required for a reaction to occur is called the activation energy. Some reactions require very little, and some need a lot more to get started. Generally speaking, most reactions will occur faster when the temperature is increased, because temperature is the average kinetic energy of the particles. With more kinetic energy, they will be more likely to have enough activation energy for the reaction to occur. But for some reactions, there is still one more factor: orientation. Even if the particles collide with sufficient speed, if they aren't at the correct angle, a reaction won't happen. In this example of nitrogen monoxide and ozone, the reaction didn't occur because the oxygen of each molecule touched during the collision. In this collision of the same two molecules, the nitrogen touches an oxygen and the reaction occurs, making oxygen and nitrogen dioxide. The orientation was correct, so the reaction could occur. So in summary, the three key ideas of collision theory are that particles must collide to react, they must have sufficient energy to break and make new bonds, and they must collide with the correct orientation. Thanks for watching this episode of Teacher's Pet. Don't forget to like and subscribe and follow me on Twitter at SciencePet.
Okay. To review, the three things that have to happen for a chemical reaction to occur is, first of all, those molecules or particles must collide with each other inside of a container. They must collide with sufficient energy in order to cause a reaction to occur. And they have to collide with a particular correct orientation. And this third piece is going to be incredibly important when we start talking about organic chemistry. So let's take a look at some graphs of activation energy. So as stated in the video, activation energy is defined as the amount of energy reactants must gain in order for a reaction to occur. This looks a little bit different in both endothermic and exothermic processes. So what you see here is a little graph for an endothermic reaction. You might remember from our thermochemistry unit. Energy is on the y-axis. The direction of reaction or time is on the x-axis. And from where the amount of energy in the system begins to the top part of this hump here, the difference between those two places is considered the activation energy. This is the amount of energy that the particles have to overcome for a reaction to occur. So notice that when that optimal amount of energy is released, energy in the system is released to the surroundings, And the products will end up having more energy than the reactants in this particular case because the reaction is endothermic. Here's an exothermic process. So you might remember this again from our thermochemistry unit. Energy is on the y-axis, direction of reaction or time is on the x-axis. So here's your initial amount of energy here. The amount of energy will increase over time until the optimal amount of energy is gained by the system. And then there is a release of energy into the surroundings where the energy of the products will be less than the energy of the reactants. So again, the change of energy from the beginning of the reaction to the maximum amount of energy gained by the system is defined as your activation energy. And when that activation energy is reached, there is a release of energy into the system. In an exothermic process, the energy of the products will be less than the energy of the reactants. Let's look at a couple of possible ways of lowering the activation energy in a system. First way we can do this is by the addition of a catalyst. So a catalyst is described as something that lowers activation energy and speeds up the course of the reaction because you don't have to take that much time to gain the correct amount of activation energy for the particles to collide with correct orientation and energy to create products. So this is going to be an example where we're going to have that synthesis reaction of carbon dioxide and water to make carbonic acid. So we got two different activation energy diagrams here. One without a catalyst. The catalyst in this case is called carbonic anhydrase, and it's an important enzyme that is contained in the red blood cells of mammals in order to convert that carbon dioxide and water to carbonic acid. Without that enzyme, it takes a lot more energy for the water to react to the carbon dioxide to make the carbonic acid. But with the presence of that enzyme in your red blood cells, it takes a lot less energy to get the optimal amount of energy between particles with the correct orientation in order to create that carbonic acid that can be flushed out of your system. So before the carbonic anhydrase, we have a higher activation energy. And after the carbonic anhydrase is added, we have a much lower activation energy, which speeds up the course of the reaction. So here's my pun of the day. Dare I say that the addition of a catalyst into a system will flatten the curve. Kind of a COVID pun. Ha ha ha. Please roll your eyes at me. That's fine. What else flattens that curve? Well, temperature will also do that. If I increase the temperature of a system, I will increase the kinetic energy of each of those particles. That means that I will increase the probability of those particles to collide with each other with the correct orientation to make products. So we're going to watch this quick little video about a Maxwell-Boltzmann distribution and what it plots and how we can see how temperature will decrease the activation energy in a particular reaction.
We'll have a quick look at the Maxwell-Boltzmann distribution curve. And here it is, and it shows the number of particles that have a certain value of kinetic energy plotted against the values of kinetic energy. So on the y-axis you have the number of particles with kinetic energy E, and on the x-axis you have their value of kinetic energy. The area under the curve shows the total number of particles in the sample. And at a certain temperature, the particles in the sample have a range of kinetic energies. On this distribution curve, we have this red arrow, which is the activation energy. And the activation energy is the minimum energy that particles must have for a chemical reaction to occur. So the white area, which is this large white area here, that shows the proportion of particles that do not have enough energy to react. They have energy less than the activation energy. The blue area here, shows the proportion of particles that have enough energy to react. They have kinetic energy greater than the activation energy. So now we'll have a look at the effect that increasing the temperature has on the rate of a reaction. Here we can compare the two Maxwell-Boltzmann distribution curves for two samples of gas, one at 300 K and one at 310 K. The area under the two curves is equal, as it represents the total number of particles in the sample. And we have this blue area, and we have the shaded area here. The blue area represents the number of particles with energy greater than the activation energy at 300 Kelvin. The shaded part represents the number of particles with energy greater than activation energy at 310 K. So as you can see, at 310 K, there's a greater proportion of particles that have energy greater than the activation energy. So increasing the temperature increases the average kinetic energy of the particles in a sample of gas. At 310 K, a greater proportion of particles have energy greater than the activation energy. Therefore, the rate of reaction increases.
Something in the video that I don't think they did a good idea of explaining is that the area under the curve will remain constant because the concentration of all of the reactants and products are always going to remain the same. The probability of those particles having the correct amount of energy to cause a reaction will just shift towards the right and meet that activation energy threshold that is on the right side of the graph. So this is going to be the end of part 1, talking about activation energy and looking at some graphs that explain activation energy. You'll see some questions at the end of the video that you might want to answer to just solidify your understanding, and then we'll move on to doing our calculations.